Okay, welcome back to gas laws. This is going to be a section 14.2 lecture where we actually talk about the gas laws themselves. So we're going to start with gas laws are mathematical representations of the observed relationships among the pressure, volume, temperature in Kelvin, and quantity of a gas. If you have not yet watched the lecture on Kelvin temperature, then you need to stop right now and go back and do that so that you can understand what the Kelvin temperature is and understand the idea behind the absolute temperature scale. All right. Okay, we're going to start with Boyle's law. Boyle's law is the pressure-volume relationship, and that statement is when the temperature and number of moles of a particle are fixed, the pressure-volume product yields a constant value. In other words, pressure times volume is a constant. Now, this is a particular kind of relationship. This is called an inverse. It's an inversely proportional relationship. And that means that as the pressure increases, the volume will decrease because anytime you multiply those two numbers, they're going to equal some constant value for a pressure. So let's say you have a constant of 4. This is whatever it is. Now, if your pressure is 4, then you're going to have to multiply that by 1 for your volume to keep that number of 4. But if your pressure goes down to 2, okay, so if we cut your pressure in half, your volume is going to be this 2 times 2 equals 4. And so if we cut the pressure in half, we would have to double the volume. All right, let's say we cut the pressure in half again. What would have to happen to the volume? It would have to double. And if we cut the pressure in half again, if we had half of the pressure, then the volume would again double. So 1/8 times 1/2. And so this is the inversely proportional relationship. And on a graph, it looks something like, let's erase all this. On a graph, it'll look something like that. So as the pressure versus volume, as the pressure goes up, the volume goes down. As the pressure goes down, the volume goes up. Okay, so that's the idea behind an inverse relationship, and that is what Boyle's law is. And that as pressure goes up, volume goes down. The expression is P1V1 equals P2V2. And so as the pressure changes, if it goes from one pressure to another, the volume will change in the opposite direction as factors. So if one doubles, the other one is cut in half when the moles of the gas and the temperature are constant. Robert Boyle was among the first to observe the properties of air, and he trapped a fixed quantity of air. He knew how much there was. He added pressure, and he was able to measure the volume change. And when the pressure increased or the volume decreased, when the pressure increased, then the volume would decrease, and vice versa. This, again, is the indirect or inverse relationship. We double the pressure, the volume is halved, or to triple the volume, the pressure needs to be 1/3 of what was before. Okay, so let's suppose we run 2 trials for a fixed gas set temp. Since the pressure times the volume equals a constant, we'll call it a K for right now, then P1V1 for the first set of conditions equals K, and P2V2 for a second set of conditions also has to equal that same K. Therefore, P1V1 is going to equal P2V2. Okay, so this is Boyle's law. And so here's our first example of Boyle's law. We are going to take, let's say we have a pressure volume of a gas. Let's say we have 500 milliliters of a gas, and we want to see, and currently it is at 2 atmospheres of pressure. Okay, so volume equals 500 milliliters, and our pressure equals 2 atmospheres. What volume would it occupy if we increased the pressure to, say, 5 atmospheres? So we have V1 equals 500 milliliters. We have P1 equals 2 atmospheres. Now we're going to change this so that we want to find V2, how many milliliters will it occupy, if we change its pressure to 5 atmospheres. Well, that means our V2 equals, don't know, and our P2 equals 5 atmospheres. Well, we would then take these values and we set P1 V1, P1 V1 equals P2 V2. Or, that would be 2, our pressure is 2 atmospheres times 500 milliliters. It's going to equal our P2, which is 5 atmospheres, times V2, which we don't know. So if we're going to solve for V2, we divide by 5 atmospheres, divide by 5 atmospheres, and we can start canceling units. The atmospheres will cancel, and I see that this 5 here will cancel with this 5 over here, making this 2 times 100, which means our V2 would wind up being 200 milliliters of gas. And so look at what happened. We had 2 atmospheres, we had a pressure of 2 atmospheres, and a volume of 500 milliliters. As the pressure increased to 5 atmospheres, our volume decreased to 200 milliliters. And that is the inverse relationship of pressure and volume. Okay, so if we have 3 of the 4 known variables, then we can see them. And the final one we can calculate using cross multiplication. There's another way of doing this, and it's actually the way I prefer if I'm doing it myself. So here's another example. We're going to calculate the final volume of a 250 milliliter balloon at 25 degrees Celsius when its pressure is changed from 740 millimeters of mercury to 850 millimeters of mercury. Well, where do we start? We start with P1 V1 equals P2 V2. Then we solve then for our new volume once we change the pressure. And it looks like that. So where V1 equals P1 V1 over P2. And to figure out how to do this, we got to learn how to cross multiply. Okay, you need to learn how to cross multiply. That's all there is to it. This is you should not be in this class if you have not already learned this skill in your previous math classes. Now, then we start substituting from here, and our V2 is going to equal 740 millimeters, which is what we started with, over 850 millimeters of mercury, okay, times the total volume. All right, and then when we figure that out, it comes out to 218 milliliters. Okay, and that brings us to Boyle's Law, and here's what Boyle's Law looks like when we graph it out. Yeah, let's move that to the top here. All right. Whatever we have, say we started the pressure that's got 100 kilopascals and 1 liter. If we cut the volume in half, look what happens to the pressure. It goes all the way up to 200. If we double the volume out here, then our pressure then gets cut in half from 100 to 50. And it goes somewhere in between. So let's say we do, what do you think that number is going to be? That number, right here, if we have, if we have the pressure, it goes up to 1.5 times where it started. I'm sorry, 1.5 times the volume. The pressure is going to drop. So instead of multiplying by 3/2, we would multiply by 2/3, and so that's actually going to be 66.7 kilopascals for a volume of 1.5 liters. And if you multiply those, you'll get your 1 times 100 again. Okay, so that's Boyle's Law. And it's time to move on to the next one, which is Charles's Law. Okay, the Charles Law, we started with that erasing. Charles's Law is the temperature-volume relationship statement. Okay, at constant pressure, the volume of a fixed amount of gas is directly proportional to its absolute temperature. That expression is V1 over T1 equals V2 over T2. Okay, so the volume of a gas is directly proportional to its absolute temperature, meaning that as the volume goes up, the temperature needs to go up, or if the volume goes down, the temperature has to go down. Where the moles of the gas, and this time the pressure, are constant. Which brings us to absolute zero, which we talked about on the Kelvin scale. This is how we discovered it. Charles was actually the one that first suggested absolute zero. And it can be theoretically reached where the volume reaches zero. So since V over T is a constant, and V over T is a constant, therefore that's how we get V1 over T1 equals V2 over T2. Okay, so if we were to reduce our temperature all the way down to zero, the volume of the gas would have to keep decreasing all the way to zero also. Okay, so our example is determine the volume of a fixed quantity of gas when its initial conditions are 25 degrees Celsius and 400 milliliters, and its final temperature is 50 degrees Celsius, and the pressure is constant. Well, V1 over T1 equals V2 over T2. Therefore, and what are we looking for? We're looking for, okay, what's our, so we've got a given at 25. We've got a given at 25. And we've got a given at 400 milliliters. So those are first, this would be T1 and V1. And we have a final temperature of 50, which is going to be T2. So therefore, our V2 is going to equal V1 T2 over T1. Okay, so here's our cross multiply. And I'm going to demonstrate this once for you guys, and you will need to follow suit. V1 over T1 equals V2 over T2. To solve for this, we will cross multiply V1 times T2 and T1 times V2. That will give us V1 T2 equals T1 V2. The order doesn't matter, it's just multiplication. To solve for one of them, so in this case we're looking for V2, we will divide by T1. Divide by T1, and those cancel, leaving us with V2 equals V1 T2 over T1. That's how cross multiplication works. This is different from cross canceling, which is what we do when we are multiplying our our units and trying to cancel those. Okay, so we got rid of those, and because they're getting in the way, and or about to get in the way, and we'll move on. So gas law temperature calculations, however, must be in Kelvin. So we have to calculate what our temperatures will be in Kelvin. This is absolutely crucial. Our things must be in Kelvin. We must have our temperature calculations in Kelvin. It's got to happen. I cannot emphasize this enough. This is a deal breaker. This is an absolute deal breaker when we work on tests. Gas law temperatures must be in Kelvin, and that was, yeah, there we go. They have to be in Kelvin. Did I mention they have to be in Kelvin? They have to be in Kelvin. Okay, so our temperature 25 Celsius, we're going to add 23 to that to give us 298 Kelvin. And our temperature of 50 Celsius is going to be, we're going to add 273 to get 323 Kelvin. And look at what this does to the pressure. Instead of a doubling of the pressure, because we doubled the temperature, absolute scale is not that much of a difference. And so it's going to increase our pressure or volume from 44 milliliters to 434 milliliters. Which brings us to the next gas law, which is Gay-Lussac's law, and yes, he's probably the most unfortunately named, in modern times, the most unfortunately named scientist that we deal with. His name actually is Gay-Lussac. His statement is the pressure of a confined gas is directly proportional to its absolute temperature. And that would be P1 over T1 equals P2 over T2. Okay, Gay-Lussac's law, then P1 over T1 equals P2 over E2 says this, that the moles of the gas and the volume are constant, but as the pressure goes up, the temperature also goes up, which makes sense. If you increase the temperature in something, the more pressure you'll have. Then there's Avogadro's law, and this is the amount-volume relationship. So equal volumes of any gas at the same temperature and pressure contain an equal number of particles. That expression is N1 over V1 equals N2 over V2. In other words, our number of moles, or the ratio of our number of moles to our volume, is always going to be constant. Now, we've discovered this before, and we've talked about this, that 1 mole of any gas has a volume of 22.4 liters. We did that through our stoichiometry unit. And so, if we have 2 moles of a gas, then that tells us that we're going to have twice the volume, which makes sense back with our stoichiometry, because we always know that since every mole is 22.4 liters, we throw that back on Mole Island, and if we double the number of moles, 2 times that number of moles is going to give us, twice the volume. Okay, which finally brings us to Char Boyles Law, which is really just an amalgamation of the names of Charles and Boyle. But before we do that, we're going to try and make that up on our own. And so here are the relationships that we have so far. We have pressure and volume are inversely proportional to each other. They will equal a constant. We have Gay-Lussac's law that says that the pressure and the temperature also equal a constant, that they are inversely proportional with each other. We have Boyle's law that says that volume and temperature will equal their own constant. And then finally we have Avogadro's principle, or Avogadro's law, where the number of moles and the temperature all equal a constant. Now, if you look at all these relationships, you can tell, or you can sort of see a pattern here, that certain things go on top and certain things go on the bottom. Oh, I'm sorry, I messed this one up. This is not T, this would be V. Well, if we were to write this where all the things, certain things go on top and certain things go on the bottom, we could combine this to make PV over NT would equal some other constant. And sure enough, this constant actually has a name, and this is called the ideal gas constant. And we will get to this a little bit later. But the idea is that these 4 all have their own relationship to each other. But even before that, let's say that we have a certain number of moles, and the certain number of moles doesn't change. We're just talking about the change of a gas. This is the change in the status of a gas. So if we change the pressure, or we change the volume, or the temperature, but the number of moles stays the same. We're dealing with the same gas, and so if we don't change the amount of the gas, we can manipulate the other things. And so what happens is, we have initial conditions of pressure times volume and temperature, and so we have Boyle's law, Gay-Lussac's law, and Charles's law, all rolled up into one combined formula. And this is called Char Boyles Law. Even though Gay-Lussac, just because Gay-Lussac doesn't combine as well with the other 2 guys, but he's in there. And that if our status of our pressure times volume of our temperature changes, okay, then it also so happens that our new pressure, volume, and temperature, different from what we started with, 2, 2, and 2, we're going to get this combined gas law, or the Char Boyles law, where the pressure and the volume and the temperature that we start with something equals the pressure, volume, and temperature that we finish. This is a change in the status situation. if we have the same gas, okay, where we're dealing with the same gas and we're not changing the amount of anything. Okay, we're going to deal with the actual status of a gas rather than a change in the status. We'll get to the actual status in a little bit later. So let's move on to Char Boyles Law. Okay, the statement for Char Boyles Law is the following: when a gas undergoes a pressure, volume, and temperature change, it can also produce a constant when the number of particles is fixed. And we just talked about that. That if the number of particles, if the amount of gas we have doesn't change, okay, so the number of moles or the mass of the gas doesn't change, then this expression holds. This P1V1 equals P2V2. This still holds. Okay, and here's our example. Determine the volume of a fixed quantity of gas at STP. Ooh, what's STP? STP is now 1 atmosphere and 0 degrees Celsius, also known as 273 Kelvin. This is standard temperature and pressure. Standard temperature and pressure. Standard pressure, standard temperature. Determine the volume of a fixed quantity of gas at STP when its initial conditions are 40 degrees Celsius, 1.2 atmospheres, and 325 milliliters. Well, okay, since let's make sure I've got this here. All right, since P1 V1 over T1 equals P2 V2 over T2, okay, we can rearrange this so that, remember to cross multiply, P1 V1 times T2 all over P2 and T2 is going to equal our new volume at T2. STP means this temperature and that pressure. Our T1 of 40 degrees Celsius is going to convert to 313 Kelvin. So, I need to erase a lot of the stuff here, so let's pause for a sec. Okay, and so, with this, our new temperature, then we're going to get our V2 to equal, and it's going to be long, okay, P1 was 1.2 atmospheres, V2, now let's do this on a separate sheet here, because this is going to be too big. So, let's erase this, and so we have V2 is going to equal 1.2 atmospheres times 313. Oh, I'm sorry, that's not right. We have P1 V1. Okay, that volume was 325 milliliters. And T2, which is standard temperature, which is 273 Kelvin, all over T2, which is 313 Kelvin, and P2, which is, this is T1, and P2, which is 1.0 atmosphere, because that's our standard temperature and pressure. Now, we multiply this out, crossify the atmospheres, cross-cancel the K's, and we are left with our number of millimeters. And so we pull out our calculator and we do 1.2 times 325 times 273 divided by 313 divided by 1.0. Remember, I like to divide by my things separately so as to not confuse the calculator. And we wind up with a volume equaling 340 milliliter. And that's what we would put over here, where volume equals 340 milliliter. Which brings us to our last gas law, and this is Dalton's law of partial pressures. And this really makes much more sense than it may in its title. The statement is, the sum of the partial pressures of all the components in a gas mixture is equal to the total pressure of a gas mixture. So the partial pressure is the pressure exerted by each component of a mixture of gases. Okay, the expression is the total pressure equals the pressure of one gas plus the pressure of the second gas plus the pressure of the third gas plus the pressure of so on and so on. Okay, so the example is determine the pressure of nitrogen in a mixture of three gases where the pressure of oxygen is 152 millimeters of mercury, carbon dioxide is 8 millimeters of mercury, and the total pressure is 756 millimeters of mercury. Well, because the pressure of nitrogen plus the pressure of oxygen plus the pressure of carbon dioxide all equals the total pressure, then the nitrogen is going to equal the total pressure minus the oxygen minus the carbon dioxide, or 756 millimeters of mercury minus 152 minus 8 will give us 596 millimeters of mercury. But here's really what that looks like. If we have let's try that again. If we have 100 kilopascals of this gas and 250 kilopascals of this gas and another pressure of this gas, when we put all of those particles in together, notice how there's the greens and there's the pinks and there's the blues, and we cram them all in together, then we wind up with this 100 kilopascals plus this 250 plus that 200 is going to equal the 550 when all of the gases are in there together. Which should make sense that the total, because we're increasing the number of particles, and we're trying to keep it all in the same container, so the volume's not going to change. Okay? And if they're all the same temperature, the temperature's not involved, and so it just starts increasing the pressure because we're just adding more gas to it. Okay? And that is Dalton's law of partial pressures. That concludes 14.2, our lecture through all of the main gas laws. We will get to the ideal gas law in 14.3. And this, therefore, is P-Dog signing off.